In the previous video, we talked about Daniel's situation where he's pushing the two crates, one in front of each other, across the ice. And we got through parts A and B where we drew the force diagram and then used that force diagram to figure out what the net force would be as he's accelerating the crates forward during the first 5 seconds. During this video, we'll be going over parts C and D, which will include the force when he's pushing it at a constant speed of 1 meter per second, and what also happens when they release the crates at the end of these. So we'll go ahead and scroll down to where we have another copy of the force diagrams, which we'll be using in this part. The force diagram general idea will still apply, but the numbers may be a bit different, so I've cleared off the values so that we can start them fresh. So, in the previous video, we started with net force. We wanted to find the net force because that would give us something that would relate to the individual forces we're trying to figure out different values. We can do the same kind of thing here, where net force is again going to be equal to mass of an individual crate times its acceleration. In this case, however, the acceleration is going to be different. We can see from the question that the boxes are moving forward at a constant speed of 1 meter per second. Because the speed is not changing and direction is not changing, this means that our velocity is constant, and therefore the acceleration, which is the rate of change of velocity, is going to be 0. What this means for us is that no matter what the mass is, so even if we go ahead and plug in the mass of 55 kilograms, multiply that by 0 acceleration, we're going to come out to a force of 0 newtons. So the net force here is going to be 0. This is different from the previous problem where we had a non-zero net force and had to use that as we went on. So now that we know that the net force is 0, let's go and take a look at what we have for the individual forces. We again know that the friction force is going to be the same 54 newtons, so we can put that for each case. And again, it's still going to be negative because it's going in the direction of opposing motion, which is our backward direction in this case. Based on this, we can go ahead and start setting up calculations similar to how we did before, using the net force and individual forces that we know. Again, we're going to have to start with box B because we know the net force for that, and we know one of the individual forces, meaning there's only one we don't know for that one. We'll set up the calculation, which would look like negative 54 from the friction force plus the box A force, which is unknown at this moment, will equal the net force. And as we said, the net force is going to be 0 because we are not accelerating. To solve for this, we can add 54 newtons to both sides. This is to isolate the box A variable here, the thing that we're trying to find. And box A will come out to equal 54 newton in this case. We can go ahead and put that on our diagram as that force being 4 newtons. Similar to the last case, box A and box B, those two forces will be an action and reaction pair. One of them is the result of box A pushing on box B, and the other is the result of box B pushing on box A. So because of that, they should have equal values, opposite directions. In this case, that means that the box B force on the A diagram is going to have a negative 54 Newton force because it's going to be equal to the 54 Newton force on the other diagram, but opposite in direction. This is going to give us the information that we need to find the push force, which is what we were asked for. So we can set up another equation based around crate. And we're going to add up all the individual forces acting on A, which in this case will be negative 54 newtons for the box B force, another negative 54 newtons for the friction force, the push force, which we don't know. So those are the only three forces acting in the horizontal direction on box A. And in this case, since there is no net force, we can go ahead and put in that there is 0 Newton net force on the other side. Simplifying things down a little bit, we can combine the numbers that we do know to get negative 108 newtons plus push is equal to 0 newtons, which can then be solved for push by adding 108 newtons to both sides. When we do that, we'll find that the push, in this case, is equal to 108 newtons. That's what we're looking for in this part. And if we think about what we found in the previous part, we found that the push required while the crates are accelerating was 130 newtons. This is greater than the value that we're getting for part C, which should make sense. Because we are not accelerating the boxes anymore, it makes sense that we would require less force here. And so the answer that we're getting is a reasonable answer for this part. We'll now continue on to part D, which deals with once the boys release the crates at the other side of the ice. For this case, we're going to have to make a slightly different force diagram. And we know that we're going to have to do that because the push force is now going to be gone. We're no longer pushing the crates, and so that force will be gone. There should still be friction acting on the boxes, so we'll put in friction. And we know that's there because the boxes are still in motion, and friction is going to oppose motion. So that's going to be present there. We also do know that the friction force is going to be the same negative 54 newtons that we had before, because they're still moving in the forward direction until they come to a stop. And so we should have that same 54 newton force acting on each of them. A slightly trickier case is considering what's going to go on with the forces acting between the two boxes. And so before we had a box A force on the B diagram, pushing it off to the right, and a box B force on the A diagram, pushing it off to the left. The tricky thing here is that these forces will also no longer be on the force diagram. One way that we could justify it by looking at what we've got here is the fact that if these are the only two forces because the push force is now gone, then that would mean that the force acting on each of the individual boxes would have to be different from each other's box forces or non-zero. That's because the box A force opposes the friction force in one case, and the box B force goes with the friction force in the other case. That would result in the two boxes having different net forces acting on them, which for two crates of the same size, each 55 kilograms, would mean that they would have different accelerations. Thinking about the logic behind this situation, as long as the crates are going to be staying together, they should, then it doesn't make sense for them to have different accelerations. So we'll go ahead and take out those box A and box B forces because they don't seem reasonable to have in this particular case. And so we'll be left only with the friction forces. Because each of the crates has only one force acting on it, that force will be equal to the net force. So our net force here is going to equal negative 54 newtons for each crate. We also know that net force is equal to mass times acceleration. Plugging in what we know for the mass and the force, we should be able to solve for the acceleration using the slightly different version where we divide both sides by mass, giving us that net force over mass equals acceleration. In this case, that means that we would have negative 54 newtons over 55 kilograms equals acceleration, and the acceleration would be equal to approximately negative 0.98 meters per second squared. We are trying to figure out how long it will take for the crates to stop. And so let's think about what we know at this point. We know the acceleration acting on each of the crates. We also know that they're going to a stop, which means for us that the velocity would be 0. Looking up to the previous parts of the problem, we know that they release them when the boxes are going at a 1 meter per second speed. So this actually tells us the other velocity, the velocity that they start at. Because we know the acceleration, the final velocity, and the initial velocity, we can use this equation for motion unit to solve for time. Final velocity minus initial velocity, all over acceleration should be equal to time. Because the crate starts moving at the beginning of this time period at 1 meter per second, that will go in for the initial velocity. It ends up stopped, meaning that's our 0 meters per second. We'll put this over the acceleration of negative 0.8 meters per second squared. And this is equal to our time. The top part would come out to -1 once we simplify, and when we divide that by another negative value, we should end up with a positive value, which makes sense. The time should be going in the forward direction, so we should be getting a positive time here. And the actual time that we end up with is about 1.0 seconds with rounding. And so that would mean that it takes us about 1 second for the crates to come to a complete stop after the boys release them. That takes us through what we need for part D and completes Daniel's problem.